I have made 16 videos in the Nerds series about a box with 2 crystal filters in it to make a selective amplifier and an oscillator out of that. Most of them with problems that were present with just 1 crystal filter. The advantage of using 2 crystals is small, 3 decibels only below 2 Hz offset, and no advantage above 5 Hz offset. When measuring the Q of the cascaded filters, I find that series connecting 2 crystal filters increases the Q by a factor square root of 2. And since noise is proportional to 1 over Q squared, I should expect a reduction by a factor of 2. That's the 3 decibels that I have observed. When I started this experiment, I had an intuitive feeling that the advantage would be greater than that, but this has turned out to be wrong. Here is a paper showing how to get reduced sideband noise by using several oscillators, all phase locked to a common reference. The reference at the center and the 6 oscillators are locked to it. This means that the phase noise within the locking range is the phase noise of the reference, but outside the locking range, the carrier is coherent between these oscillators, while noise is uncorrelated, so there is a possible improvement by a factor of 6. And if the reference oscillator were included, it should be a factor of 7. Here is the result at 10 MHz. The red curve is a single oscillator here, and it is about minus 170 dBc per hertz. With 6 of them, it's approaching 182 or 3 or so. But at frequencies below about 10 Hz, performance doesn't differ between a single oscillator and all 6 of them. As expected, of course. In this video, I'm going to try a different approach to try to get the advantage of a factor of 3 reduction in the sideband noise. This might look a little bit peculiar, but I will show the equivalent schematic diagram. At the frequency of resonance, each crystal is equivalent to an inductor in series with a resistor. And then the amplifier, it has an input impedance. And I have to make the input impedance of the amplifier significantly lower than the series resistance of the crystal, because I want a high loaded Q. The crystals I will use are specified like this. Series resistance about 80 ohms and the Q about 1.25 million. With a crystal resistance of 80 ohms and Q equals 1.25 million, I can use the formula to compute XL, the reactance of the inductor, to 100 megohms. Then, assuming different values on the input impedance of the amplifier, 40, 20, 10 and 5 ohms, I can compute the Q with the increased total resistance, 120, 100 and so on. And I get these Q values. This is the percentage of the unloaded Q. And then I can see the loss in near frequency performance as compared to the unloaded Q, half a dB, 1 dB, 2 dB, and 3.5 dB. In the far range, where the flat noise floor is. The loss through the filter is the important aspect, and that is 40 divided by 120 and 20 divided by 100 and so on. That gives me these losses compared to a lossless filter. Now, I think the reasonable compromise would be 10 ohms. So with respect to the performance here, I can see that going up to 20 ohms will give me 2.6 decibels better far range noise floor, but 1 decibel worse close range. And 2.5 dB loss at close range would give me 4.8 for the flat noise floor. And on the other direction, going down to 5 ohms would improve the close range by 0.5 dB, but degrade the flat noise floor by 2.8 dB. Now, to this, of course, comes noise from the amplifier and maybe other noise sources. I have made an amplifier like this. It has very interesting impedance properties. I have calibrated the network analyzer with open and closed and the reference load through a female-to-female adapter to the male BNC, which I will then connect to the test object. When I connect open, the impedance level is about 35 kilo ohms. And what I see is, of course, the noise in the system. I have a low power level, minus 40 dBm, because when there is no load on the amplifier and I want to measure the input impedance, there is a great risk of saturating it. When I disconnect the female-to-female adapter and the open connector, I get a different result. The impedance now is about 7 kilo ohms, and that is because the small capacitor is missing. That is an imaginary component, and I can change the electrical delay to optimize or to compensate. Oh, here we are. Minus 67 millimeters is what this instrument suggests. But the thing, I can compensate for reactive loads by tuning the electrical delay. I'm now looking at the amplifier output with the input open. And at 10 megahertz I see 3.9 kilo ohms. I will eliminate the reactive part. At 10 megahertz it is minus 118 millimeters at 10 megahertz, and it depends on the frequency, and the associated real part of the impedance is 30 kilo ohms, means very, very high. I will connect a crystal in parallel with an inductor that compensates for most of the capacitance of the crystal. The sweep is 1 megahertz. I will make it much smaller so we can see what happens at the crystal resonance here. Now the sweep is 1 kilohertz, and I will make it even smaller, just 100 hertz. And at the bottom the impedance is 676 ohms. I can change the scale, 500 ohms per division. And then I see I wasn't exactly at the bottom, but 670 ohms. So it goes from 30 kilo ohms to 600 ohms. That's a very big impedance change. Here is the input impedance with the output open. And I had to set the electrical delay to minus 412 millimeters to eliminate the reactive part on the input under these circumstances. And then the impedance is 3 kilo ohms. And the frequency range is now 1 megahertz. And I have connected a 100 ohm resistor on the output, and that makes the input impedance much lower. It says 17.6 ohms here. And after I change scale, I can see that it is flat 17.6 ohms over 1 megahertz. With 50 ohms on the output, I see 12.5 ohm on the input. And finally, 25 ohms on the output gives 10.35 ohms on the input. Now that I know the impedances, I can figure out what power to expect in the output load. I have 3 cases, 100 ohms, 50 ohms and 25 ohms. And for them, these are the input impedances of the amplifier. I can compute the power that goes into the amplifier, knowing that this is the schematic. The impedance of the crystal, the inductive part, doesn't matter. The resistive part is 80 ohms, and I am allowed to dissipate 0.1 milliwatt. That's the maximum according to the manufacturer. And then I have the impedance of the amplifier, which can take these values. So the power developed in the resistor here, the input of the amplifier, is the ratio of 80 ohms to the input impedance, because the current is the same through both of these resistive parts. So I can compute what is the voltage across the input impedance, and it comes like this. And I have now set these voltages to the amplifier while having these resistors at the output, and then I can measure what is the voltage across these resistors, and from that I can compute what is the power in that resistor with this formula. So I see that if I use a 50 ohm amplifier as the second amplifier stage, I will have 0.8 milliwatts in it when running the crystal at its maximum permitted signal level. When I connect 3 of these crystal and amplifiers in parallel, they will give the interesting signal will be in phase, so it will add with 3 times as much current to 3 times higher voltage. But the noise presented by the crystal and the amplifier, that will be uncorrelated, so it will present a current that is the square root of the sum of squares. So that is from where the advantage of having 3 separate crystals and amplifiers come. There is the gain with the square root of 3 in signal to noise ratio. I have used the tiny PFA to measure the phase shift through the amplifier. Twice I have used just a female to female adapter, means measuring nothing, and then I get this red and blue curves. And then I measured with the unfiltered power supply and with a filtered power supply. And at 30 seconds I see the same here, and the difference is very small. And uncertainty becomes great at 1000 seconds because I would have to use a much longer measurement time to get a reliable result here. I can compare this with what I found in nerds104, which I have here. And I have placed the graphs so, for example, 10 to minus 15 is the same, 13, it's the same, and on the horizontal axis 10 seconds, 100 seconds. So we can compare directly. In the video, my measurement of nothing, the red curve, comes here. And now the result is a little bit better. I have tried to improve my setup. Then the result of the amplifier at 30 seconds comes at the same place where I had it in this previous video. 10 seconds. Here it is much better, but that's because my system is better. Probably. And at 100 seconds, it's the same. I have restarted collection of phase data. The unit was quiet for a while. It took 10 minutes about for the system to stabilize. I am measuring the phase shift through the box, and now I will do like this to change the temperature. And I do this for half a minute. And this had a significant influence on the phase shift, as you can see here. Whether it is the box, what is inside, or if it is the cables to and from the box that make this difference, I don't know. But this indicates that the problem I see are not really of electronic nature. The time scale is 1 division for 10 minutes. If I move from the first here to the next, you say 10 minutes and 10 minutes. So that waving with some sheet of paper, it took 10 minutes before the effect of that has disappeared. Now I do a different thing. I changed the supply voltage here by 10 millivolts. And here is the effect. There is a RC filter, so it takes some time until the voltage has changed in full. If the noise I see, amplitude here, were caused by supply voltage variations, it would be in the order of plus minus 1 millivolt. But the supply voltage is far more stable than that. It is varying less than 0.1 millivolt. The last two digits go between 29 and 30. And I have looked at it for a long time and it stays steady like this. Now the change corresponds to maybe 3 millivolts. Now here is the alarm deviation for nothing and for the amplifier. And when I look at the phase difference, we see a very obvious difference. Here is some noise, and it must come from the amplifier. I don't think it can come from the cables. But the level is low enough to not be a problem if I compare to what I found in the nerds104 video. The horizontal scale now is 1 minute per division. 19.34, 20, 31. So 1 minute per horizontal. And then structures like this, they occur over time scales of several minutes. Say from here to here is 4 minutes. If I zoom out, you can see that this is the typical. So these are slow variations, and I don't know what could be the cause. maybe it is flicker noise in the transistor. 1 over F. I don't know at what point if F is 0, the noise would be infinite, which is obviously not correct. But maybe it is working, this 1 over F noise problem, all the way down to several minutes. I have replaced the BF240 by a BCY59, which is a switch transistor supposed to give low noise at low frequencies, but transition frequency is 100 MHz, so it's okay at 10 MHz. But what I observed is a much higher flicker noise. I assume it is flicker noise, and I assume it is causing the capacitance of the device to change. And since BCY59 has a higher capacitance than BF240, I have a worse situation. That is a hypothesis I will thus test. Now, when changing transistors, I also change the operation point. That is to allow a larger voltage across the emitter resistor to have more feedback for variations of the current through the transistor. And further, I changed the resistors from carbon film to metal film. So I have to go back to the BF240 with the new resistors to see whether that had any effect or if it is only the change of the transistor that matters. When I look at the phase versus time, I can see that the blue curve here, which is the BF240, is not as noisy as the green one. Now the BF240 is connected again, and it is much better than before. It's the green trace, and this was what I had previously. And I don't think the change from the operating conditions, going down from 9 volts to 6 volts for the base collector voltage and increasing the current, I do not think that could do anything, or at least not as much. So the difference, the big noise I have here at 30, 40, 50 seconds is because of using carbon film resistors instead of metal film resistors. That's what I think at this moment. I have reduced the emitter resistor by a factor of 2, from 360 to 180 ohms. That has increased the current from 15 milliamps to 30 milliamps. And this has not been good for the Allen deviation. As you can see, the traces are significantly above the black trace, which was what I had with 6 volts, 15 milliamps. But there is something funny behind this. The 3 measurements were made directly after each other. The first one is this, and then this one, and finally this one. They all slope the same way, and it's over a long time. So this cannot be temperature. I think it's an aging phenomenon. The transistor is now a bit warm, not really hot, but significantly warmer than the surroundings. And I think something is aging inside it. So I made a test. I placed a cooler on the transistor, and that changed. It still slopes the same way, but suddenly it has stopped with that. Looking at the Allen deviation, this is what I see, and now it is better than the 15 milliamp situation. I don't really know what to think about this, but it seems keeping the transistor cold is an important thing. I want to know the sensitivity of the phase with respect to the voltage, so I step up by 0.1 volt here. The step was at 92 seconds. And here at 243, that is 2.5 minutes, I see 1.87 times 10 to minus 11. This gives me 1.87 times 10 to minus 10 seconds per volt. Now I have looked for 2 hours and 43 minutes. The green curve looks very odd. Excellent performance. Then it starts to drift at a fairly rapid speed. And then it's constant. And then again it decreases. Increasing the voltage went the other way around, which means that this corresponds to an increasing capacitance in the transistor for some reasons of aging or whatever. Or it could be something else. I have no idea what the reason is, but this cannot last forever, I think. So probably if I waited long enough, these events would no longer occur. Anyway, the Allen deviation is pretty good. It is close to what I'd had with nothing connected, but at times above 200 seconds, then we have the effect of these funny phenomena. I have replaced the BF240 by a BFR91A. That's because I thought that a smaller output capacitance would make the capacitance variation smaller when the supply voltage is changed. But the result is a little bit surprising. The output level is now 3 decibels higher, and the noise is significantly lower. It is the green curve, and it is a straight line all the way up to 200 seconds, and significantly better than the cooled BFR 240. Of course, the BFR 91A also has a cooler on it. When I look at the phase versus time, this looks very nice as compared to the BF 240, which had this odd behavior. Here I have changed the supply voltage by 0.1 volts. Starting at 60 seconds, the behavior is quite different from the BF 240. It goes straight up and then it stays constant. There is not the time constant I saw with the BF 240. Anyway, the change is phase here is very close to 0, and after the step it is 2.11 times 10 to minus 12. This is 10 times better than the result with the BF 240, which gave me 1.87 times 10 to minus 10 seconds per volt. And here I have 2.11 times 10 to minus 11 seconds per volt for the power supply voltage. So it's a big improvement. When the output is open, the input impedance is now capacitive. If I tune it out by changing electrical delay, I can read the real part as 1.9 kilo ohms, so that's very high now. With 50 ohms on the output, I then see 8.5 ohms on the input. That's much lower than before, but I still have the electrical delay set to 2.9 nanoseconds. If I set it to 0, I see that it is inductive, but still very low. Here is the original design after the modifications I made to it. putting the BFR 91A and changing these resistors. This is now 180 ohms. The binocular core with material 65 has permeability 100. Now this material cannot be obtained anymore, so the next transformer I made was using material 67, which is available now. It has lower losses but significantly lower permeability, only 40. To lower the output impedance and increase the impedance on the input, I made a tap on the collector coil, and then because the permeability is lower, I have to tune the coils now. So there is a small capacitor here, just a few PF, and to tune on the other side I have a series capacitor here to make the impedance real at both ends when the other end is open. I have connected a crystal to the input, and then I see that the impedance level is about 9.5 kilo ohms here. And on the resonance I have to change the frequency scale. On the resonance I see 193 ohms. The gain of the amplifier coming after the first stage will depend on the impedance. The greater the impedance ratio, the better suppression of the flat noise floor. And here I span 10 kilohertz, so I can see that plus minus 1 kilohertz from the carrier. Then the gain of the next amplifier is determined by the ratio from here to here. That ratio is now 49.2. With the previous coil and design, that ratio was 44.8. So there is an improvement, and I think that is because the material 67 that I'm using now has lower losses. But there could be other reasons also, I don't know for sure. Here is the input impedance, 13 ohms, while I'm loading the output with 25 ohms. The sweep is 2 megahertz, so this impedance is fairly wideband. With 25 ohms on the output in the new configuration, I get 13 ohms impedance on the input. So I use the values from 12.6 ohms, means I send 40 millivolts peak to peak into the amplifier, and I found the output is then 157 millivolts peak to peak. That gives me 0.12 milliwatts. Previously, when I computed these values, I forgot to convert from volts peak to volts RMS. So instead of about 1 milliwatt, it's about 0.1 milliwatts. And now I have a little bit more power into the second amplifier stage when presenting 13 ohms to the crystal. Before 0.1, now 0.12. With the new configuration, I see a performance loss. The last one with the previous configuration, test 9 with BFR 91, it was at 2.76 at 100 seconds. But now with the new configuration, I made 2 measurements so far. The first one gave 4.01 and the second one 3.67. 2 hours and 4 hours respectively. When I look at the phase versus time, I see that test 9, the good curve, is fairly smooth in the time scale of from here to here to here. There is some problem. Now, when I had nothing connected, I had a similar situation, but with a slower, there is a larger distance between these peaks. When I zoom into the curves, I see that the new configuration has some oscillations with a period time of about 200 seconds. The only questionable component I have added is this trimmer capacitor. As you can see, it is close to its minimum value. I will just remove it to see whether it makes any difference. It took about an hour for the unit to stabilize. As you can see here, 3,300 seconds here. The Allen deviation shows that it's not really good above about 20 seconds. I can edit if I stop collecting more data like that. I can then select this time region, the first hour, and then go into File, Edit, and remove selected or zoomed part like that. And now it looks different. It is still a bit noisy, but the Allen deviation now looks more like the other traces. I will start again now that it has stabilized, perhaps. After 10 minutes only, I can see that the capacitor was a problem. So now it's okay again. Already after 10 minutes, I can see that the trimmer capacitor was a problem. I know that since before, but I did not know that it was so important as it seems to have been when I look here. The black curve, which is the new one, is below all the others. I will wait for quite some time because there could be problems coming that will show up later. Well, you can see already it went up a little bit to be on the same place as the test 9, which was before I made a redesign of the transformer. After 20 minutes, the situation looks a little bit different. Maybe the conclusion was not right after all. The associated phase difference looks like this, and we are getting back this wavy structure. I will wait for quite some time to see what comes next. After 4 hours and 46 minutes, this is what I see. The black curve is the same as the other curves with the new transformer, or even a little bit worse. At 100 seconds it's 4.48, while the others are a little bit below that, while the test 9, which was the last one before I changed the transformer, is at 2.76. When I look at the phase versus time, and I can zoom in on this region, for example, I can see that there is an obvious structure in the latest measurement that has been present in the previous measurements on the new transformer, but which was not present in the test 9, the red curve here. I find it difficult to believe that this structure is really caused by the amplifier. I think it is something with the tiny PFA. I have started a new measurement. This time I increased the signal level by 1 decibel at the start of the measurement. And it gave this thing. Moving the switch means there is no signal for a short time, and then the signal level is stronger, and I get the new situation, and it will take some time for probably the tiny PFA, to come into equilibrium with this new situation. I no longer think that the problem really was that trimmer capacitor. I see now all the three curves having nothing, or the new transformer give the same result. At 100 seconds 4.4, and in the last case 4.1, but it's only 1 hour there. And the trace test 9, for some reason the problem was absent, and I cannot explain that, but when I look at the phase versus time, and I pick this 1 hour, you can see this periodic thing, which is not present in the test 9, the magenta trace here. And not even if I zoom out a little bit. So this structure has some explanation, to me unknown. But when I look here, I can see it comes here and here and here. And then there is a higher frequency here and here. And then there are intervals when there is no such structure. I have introduced a significant phase shift. The cable going around like this, maybe 1.5 meters. Actually 8.7 times 10 to minus 9 seconds is the phase shift. Well, there is a difference, but in the wrong direction. If I look at phase versus time again and zoom into this, I can see that we have this wavy structure, but the frequency is different. The period time is a little bit longer now, and this cannot possibly be because of some noise produced in the amplifier. It must be caused by the measurement system. So I will just forget about this interference or whatever and decide that, well, the amplifier will be okay like this. I have placed the amplifier in my interferometer and using that to reduce the carrier by 30 decibels. And then I look at the sideband noise with the PM2060 and with Linrad's direct conversion receiver. And here is what I see. At 1 Hertz, it says minus 113, means minus 143. And that is well below the performance I can expect from an oscillator. And this is 1 Hertz is within the passband of the crystal. And exactly what it means I cannot say, but that is what I see. And the flat noise floor at 10 kilohertz, it's at minus 148, means minus 178 when I take the suppressed carrier into account. And that is perfectly okay, because at this separation, more than 1 kilohertz, the succeeding amplifier will have much less gain because it will be fed from a much higher impedance as compared to where it has maximum gain. So at least this is what I observe. When I look at Linrad, I see a difference at 1 Hertz. Linrad says minus 118, means minus 148, while PM2060 said minus 112. But there is a peculiarity. As you can see, the phase here has a discontinuity where the one of the sidebands passes DC, where it disappears. This should be something like that. Anyway, these are the values that I get. Linrad allows me to measure the amplitude noise at the same time. So I take down these values. I can look at amplitude noise and phase noise at the same time, and it's clear that the phase noise is significantly lower than the amplitude noise. And the correlation between AM and phase noise is high. The modulation is in the imaginary part, means that the modulation is phase shifted by 90 degrees between AM modulation and phase modulation. So I think the mechanism is that there is flicker noise in the transistor, and that causes amplitude variations, but also small variations on the capacitance in the transistor. So that's why they are correlated. Here I'm looking at the amplitude noise with the PN2060. At wide separations I see it very clearly, at minus 147 and then minus 146.7. This is the same as the level for the phase noise, because out here it's the white noise of the amplifier, which doesn't have any phase relation to the carrier. Then, coming closer to the carrier, I start to see flicker noise, down to 100 Hz, where it is minus 165 dBc per Hertz. Coming closer to the carrier, I cannot see it properly because the statistics is not good enough. You can see maybe the small circles on the data points means the data is not correct. And we can also see the thin line here starts to come to the same position as the thick line. The thin line is the imaginary part, and the measurement is okay down to about 80 Hertz from the carrier. So I just get the limit for where the noise level might be. I have set the carrier suppression to 50 decibels now, and then when I look at Linrad, the result is in agreement with what I had before, but for the PN2060 the result is completely absurd. At 10 kHz I can read minus 137, means minus 187, and that could not be correct. But in Linrad at 100 Hz I see minus 116 becomes minus 166. And that's the same as I had with 30 dB carrier suppression. Now I look at the phase noise with 50 decibels of carrier suppression. The PN2060 seems to be okay for phase noise, even when the carrier is well below the normal. It is minus 18 decibels and is supposed to be about plus 10. So it is a very weak carrier, and then the amplitude detection was probably incorrect, but phase detection is okay here. I take down the numbers for further comparisons. Black numbers are from 30 decibels carrier suppression, and red ones are with 50 decibels of carrier suppression. I can see at 100 Hz the numbers come out the same for phase noise, and the AM noise is the same in Linrad, but in the PN2060 they differ by 10 decibels all the way. So I think the evaluation of the carrier level as compared to the amplitude modulation is not correct in the software here. But these numbers agree perfectly well. Amplitude noise and phase noise, well, between Linrad and PN2060 there is a 5 dB difference, and even more at 1 Hertz. But the results are nearly the same at 10, and they are exactly the same at 100 Hertz. And of course, at wider separation, it's the flat noise floor, and I can get it from the PN2060. And it comes at the same level as it was with the 30 decibels carrier suppression, or nearly. The sideband modulation produced by this amplifier could depend on the values of these resistors. I have made them very low impedance, 360 ohms only, so they take a significant amount of current. I will now increase them to see if that affects the modulation, amplitude modulation as well as phase modulation. There are two mechanisms. One is the thermal noise when this resistor value goes up, and the other is there is a current flowing through here, and maybe that current has some noise in it, I mean flicker noise, and that would cause a varying voltage drop across this resistor if I make it much bigger. I have put a 47 kilo ohm resistor in series with this one and 3.9 kilo ohms in series with that one. This way I have the same current through the transistor, so I can measure the same voltage across this resistor, which I had forgotten to place in the diagram. Also, this is to prevent oscillations at several hundred megahertz, 2.2 pf and 100 ohms. And I had to add this link also when I put some not resistive load at this point for high frequencies. And I don't remember the capacitance, it's insignificant anyway at 10 megahertz. Here is what I see with 50 decibels carrier suppression. The values I see here are exactly the same as I had with the old resistors. So the impedance of the voltage divider is not important for the phase noise. And here is the amplitude noise with Linrad, and it is significantly higher than it was with the smaller resistors. I have placed a 4700 microfarad capacitor from base to ground, still keeping the large resistors. This has made a big difference. We can see already here the sideband noise is much weaker. That's of course the amplitude noise we can see here. But I can already now see the shape here is different, and I have to wait for the noise to come out from the imaginary part. This was a surprise. The big capacitor put back the amplitude noise very close to where it was with the 360 ohm resistors, but the phase noise is significantly lower now. So there must be a radio frequency component that needed to be decoupled. So I will try some other things. I have removed the electrolytic capacitor, and you can see this noise here is back. Not quite as bad as here, but it is much stronger than it was here when the electrolytic was in place. But the original base decoupling capacitor was 10 nanofarads, a ceramic disc capacitor. That was because I had problems with VHF oscillations when using some plastic foil capacitor. I have now connected parallel to it a 0.1 microfarad, which I know has its series resonance at 10 megahertz. So it gives a very good decoupling of 10 megahertz from the base, and that has improved significantly the phase noise. And the correlation between phase noise and amplitude noise is much smaller. Here it is close to zero. and here it is much lower than before. And I don't claim that I understand what's going on, but certainly it is important to decouple the bass properly. The amplitude noise now, as compared with the 360 ohm resistors, is degraded by 2 decibels at 110 and 100 Hertz. So that's a small loss. So I think I do a compromise for the resistance and avoid the big capacitor, because the big capacitor doesn't help at 0.1 Hertz offset from the carrier. I think I will have to investigate this when I have made a proper layout, because the decoupling of the base to ground raises the question, what is ground? It is the point where the coaxial connector for the input is grounded. It's far away in this little box, and maybe I have to be a little bit more careful. On the other hand, when the crystal is the source, ground is the other side of the tuning capacitor of the crystal probably. So I will go back to this. But before starting to make a proper layout, I have to check whether this added better decoupling for the base has changed the impedances. First, I verify calibration. It says 80 milliohms resistive and 29 inductive. So it is okay, although I just switched on the network analyzer. So it is stable and remembers calibration since I used it previous time. And I put 2 50 ohm dummy loads on the output to present the unit output to 25 ohms. Now the input impedance is 12.0 ohms. I had a little accident, so I had to replace the transistor. I don't know whether that has affected things. With 50 ohms on the output connector, I see 21.1 ohms on the input. Finally, with 100 ohms on the output, I see 38.6 ohms on the input. I want to measure the noise figure of this amplifier. To that end, I need a low noise receiver with 50 ohms input impedance. So I'm using the Perseus, 2 series connected preamplifiers, and a matchbox to set the impedance to 50 ohms. So it happened to come to 49.6, and that is accurate enough. I switch on the noise head, and it is in the low range and shows now 3.3 decibels. And in the lean rod S-meter graph I can read the noise floor before I switched on, 0.01, and after 3.11. So the noise figure is just below 3.2 decibels. I have converted this 50 ohm noise head to 77 ohms by adding 27 ohms in series with it. With a modified noise head connected to the input, the output impedance is about 200 ohms, slightly inductive. And when I disconnect the power supply, the output impedance goes up in the kilo ohm range. When I set this attenuator to 1.8 decibels, I have a room temperature dummy load that matches the impedance of my amplifier with the modified noise source on the input. It looks like this, slightly capacitive. And when I set it to 1.4 decibels, it is similar to what the amplifier gives when I have a 50 ohms resistor in series with its output. It should be 240, but I see 227. or 233. It's a little bit noisy. Here is the noise floor of the parcels when I simulate the output impedance of the amplifier at room temperature. And here comes what happens when I disconnect it, so it looks at the impedance that the amplifier has when the DC voltage is off. So the difference is from 0 to minus 2.2. And with 50 ohms in series, as I simulate with the attenuator, the level goes down by 1.99, means 2.0 decibels. Finally, with 50 ohms in parallel, and then I will disconnect at this point to see whether I can see any difference. The difference is very small. 50 ohms or 50 ohms in parallel with 200 ohms makes a change in the noise floor of the receive system by 0.13 decibels. That's close enough to 0. Here is the noise floor with a 50 ohm resistor connected in parallel with the output, and it's from here to here. It is 0, I calibrated it for that. And here I have switched off the power supply, and then I see minus 3.76. And here is the noise floor without any resistors involved, and I have switched off the power supply, and then I see that the level goes down by 10.75 decibels. Finally, with 50 ohms in series with the output, I have the noise floor here, and here I have switched off the power supply. And I see 9.56 decibels. The slope here is before I shorted the cable to the box, because there is a big electrolytic capacitor inside it. So it takes a long time for the impedance to go down, corresponding to 0 supply voltage, unless I short it. The noise figure is not what the noise figure meter is calibrated for, because now I have 2 resistors with different temperatures, and one of them has the temperature the noise figure meter thinks, the other one is room temperature. So the effective temperature of both of them is like this. Ask ChatGPT to know formula for things you didn't know before. From that I can compute that the temperature that is seen by the amplifier is 0.65 times the temperature the noise figure meter believes it has, plus 103, and that is in kelvins. So with noise figure 0, T1 is the same as room temperature, means twice 295, that's 590. At noise figure 5.9, T1 becomes 1042, while the noise figure meter thinks it should be 1445. So I compute the noise figure to be 4.0 rather than 5.9. And the 4.8 becomes 3.1, thinking the same way. Then there is the problem with RX noise, I mean noise from this. And that is particularly important when the 50 ohm resistor is in parallel with the output, giving me 25 ohms to be seen by the amplifier. Then I measured what happens when I switch off the voltage. That was 3.7 decibels. But out of that part was because of the changed impedance, so correcting for that gives me 2.35. And in the end, I find that the error is 1.4 decibels. At 50 ohms and 100 ohms for the output impedance, the corrected change of noise when the amplifier was shut off is significantly larger, and the corrections become fraction of a dB only, like this. Here I have collected all the information. The impedance the amplifier output is looking into, 25, 50 or 100 ohms. The corresponding input impedances as measured. Then I can compute the power developed in the input of the amplifier, PA here, milliwatts and dBm. The voltage here in millivolts, and when I send that voltage into the unit, I can measure these output voltages across the output resistor. Then I have the change in the noise floor when switching off the DC supply to the unit, and corrected it for the influence of the impedance change. Then the measured noise figure, corrected for the noise temperature of the modified noise head. That's this correction, because the temperature is not what the noise figure meter is telling. And then for the impedance change, that is this correction, because a big part of the noise comes from the receiver. This gives me the noise floor. The noise figure gives the noise floor. I assume the noise figure is 3 decibels because the accuracy of this might be questionable. The SSB phase noise then within the passband of the filter is like this. So I improve the noise floor by 5 decibels, going from 25 to 100 ohms load impedance. I don't know if this matters or not. At close range, the Q of the crystal is the dominating effect, Q squared, and that gives a loss in the close range, like this. But maybe there is an improvement because of the improved signal-to-noise ratio, even at close range. At wide range, I have these numbers. I will start looking at have a load impedance of 25 ohms in this experiment. And then I will change that impedance up and down to see what will give the optimum. This is the transformer I have been using. 9 turns with a tap at turn number 5 and a secondary with 3 windings in parallel, but just a single turn. Here is what I see on the network analyzer. It's clear that it is a little bit inductive, so it will need a capacitor to become very high impedance. It says 19 microhenries at 10 megahertz, and at 5 megahertz it suggests 16 microhenry. To see how good the coupling is, I have shorted the emitter winding, the single turn. And this has reduced the inductance to 1.8 microhenry at 10 megahertz. So the coupling is reasonable, but not really very good. Now I have shorted only one of the 3 secondary windings. Then the inductance is 2.6 microhenry. It was memory like that, 1.7. So having more parallel secondary windings improves the coupling, but it's still not very good. This is the old transformer, 9 turns and 1 turn. This was wound on the 61 material, which has higher permeability. And then, of course, inductance is much higher, 48 or 49 microhenries at 10 megahertz and 30 microhenries at 5 megahertz. I don't know why the inductance becomes lower when I change the frequency. Well, that's how it is. Permeability is frequency dependent. And then, of course, inductance is much higher, 48 or 49 microhenries at 10 megahertz and 30 microhenries at 5 megahertz. Now I see 1.6 microhenry. With the new core it was 1.8. Resistance 6.6 and here 7.3. Now I'm looking at a material 67 core with 9 turns of 0.35 mm enamel wire. This is what I see, and this is what I had with the Litz wire, and the difference is pretty small, as expected. I have now a secondary winding with a single turn, and it's shorted. Then I see 2.9 microhenry. With the Litz wire I had like this, significantly lower, means stronger coupling. I have now made the secondary from a 1 mm enamel wire. Then this is what I see. With the Litz wire I had this, and this is not as good. Note the losses. This distance to the outer circle is much larger than this, so the Litz wire was not a good idea. The secondary is now a single turn of a 1.9 mm, while the primary winding is 0.35. And this is what I see. The Litz wire, the same number of turns, was like that, far more lossy. So this must be a much better solution. Now the secondary is 2 wires with diameter 1.5 mm. It gives me slightly more copper, and it's a little bit easier to work with. Here is the result for the new with 2 1.5 mm wires, and here is the old one. So the coupling between the windings has improved. I have increased the diameter of the wire for the 9 turns winding from 0.35 to 0.45 millimeters, and the single turn is 2 wires diameter 1.5 millimeters. And now the core is full. It's not possible to squeeze any more copper into it. Here is the result. The previous with 0.35 millimeter wire was like this. Look at losses. It was 1.6 ohms, and now it's 1.36 ohms. And the inductance is 1.2, and previously it was 1.4. So this is significantly better. When the single turn is not shorted, I see 14.7 microhenries, and the resistive part comes out negative, which of course is not correct, but it means that losses are very low. I have increased the amount of iron by adding another binocular core to make the total size a little bit longer. And here is what it looks like. The previous with the normal size core was like this. Not a big difference, but the inductance has gone down a little bit now when the secondary is shorted. I have opened the secondary, so there is only the primary now, and the inductance has gone up. It was 13.7 before, now it is over 30 microhenries. So that is an improvement, I think. The inductance ratio when shorting the secondary has become more than twice as large. I have placed the elongated core in the amplifier box. The load on the output is 50 ohms. The input impedance is now 28.1. It was 21.1 with the old transformer. I have decoupled the source resistor. This is what it looked like before. So the impedance went up from 7 to 8 kilo ohms. This is on the output when the input is open. It is this resistor that I have decoupled. It made this inductor more lossy, but the inductor is 100 microhenry, so it has a very high impedance at 10 megahertz. Suddenly, the output impedance went down from 8 kilo ohms to about 4 kilo ohms. So something has gone wrong with this transformer, I think. I replaced it by the original, this one with the Litz wire, and that was as it was before. So I am looking at this transformer with the secondary shorted. And something has happened to it. Before the resistance was 1.38 ohms, now it is 3.69. And the inductance was 1.21, and now it's 1.82. So maybe there is a shorted or partly shorted turn on the transformer. I cannot think anything else. Actually, the reason why I chose to use Litz wire on the first transformer was that I was afraid for this kind of problem. I have had such problems before. Putting enameled wire into ferrite is a bit risky because the ferrite is very hard and can easily scratch the enamel. I am making a new transformer. Here I have painted the sharp edges on the ferrite with nail polish, hoping that that will protect the enamel wire. The wire this time is 0.4 millimeter of another quality. It's not solderable, and I think the isolation is harder, while the wire is softer. As it turns out, the nail polish was too soft. It didn't stay in place, so I am using this UV hardening glue instead. It seems more suited to the purpose. Now the amplifier works okay again. The impedance seems to be about 15 kilo ohms, and then there is the crystal here. At the center frequency I see 137 ohms. This that I call the crystal ratio has increased by a factor of 2. Now I'm not so sure the instrument is accurate at these high impedances, but it's okay anyway. I will fill the core with epoxy resin to make sure that nothing bad happens when I happen to bend the wires when I modify things around it. I will now make 3 amplifiers like this and do some practical things to interface them to the 3 crystals. But that will be the next video. I think this one is long enough now.